Hello, everybody. This is part 2 of, or I guess part 1B of my homework 2 for comp methods, and I am going to derive the expression for the entropy of a discretized probability distribution. I'll use an example of a student grade distribution in terms of the number of possible permutations of n objects, with the number of I objects being similar, where I is a distinguishing feature, for example, the grade. So let me boil this down a little bit more and sort of define the example a little bit more. Let's say that I put together an exam for Calc 1, and a total of 1,000 students took said exam 1. So that would be this big N right here. That's the total number of students, or the total number of data points. Now, let's also say that the number of grades, or I guess there's 10 different grades you can get. The grades can go from, say, 1 all the way to 10. So you could have, the worst score would be a 1, the best score would be a 10, for a total of 10 different grades. Now, with all this in mind, let me go ahead and pull this back up. No, this is the screen I want. Derive the expression for the entropy of the probability distribution, the distribution of the students' grades in terms of the number of possible permutations of n objects. So that's the total number of students with the number I, so that's a little ni, being similar, where I is a distinguishing feature. So that's either getting like a 1, getting a 2, getting a 3, all the way through getting a 10. So, awesome. Now that we have this, let's think about this for a minute or two. Let's say that I have this big, let's say I have this scale to look at the distribution of grades. And the scale goes from, I'll just approximate it, it goes from 1 to, skip a few, all the way to 9, 10. Well, there's a few different ways that I could potentially distribute all this information. I could go through and maybe just go with a basic, very uniform distribution. And I could say that, you know what, I'm estimating that there are 100 students in each bin. So, if I could get all my zeros in, I would just say that there's 100 students in each bin. And that's possible, right? I could also say, well, actually, I think that a lot of students did really well in this exam, and I think that maybe there were 500 in 9, and then 500 in 10. And these are just sort of like two example distributions I just came off of, just off the top of my head, just kind of made them up. But those are like two potential ways that this could be distributed. Now, what I'm going to eventually come back and do, particularly in part C, is demonstrate numerically that for a given average and standard deviation, maximizing the entropy of a discretized probability, yada yada yada, I'm going to maximize this entropy function. And so I guess what this entropy function that I generate up here. And so what I really want to get at here is that whatever this entropy function I generate is, the maximum of it should be a more normal distribution. And so I'm actually going to try to build a function for the entropy that is normalized. But the big question, I guess, that's kind of raised by this is, what is entropy? Right? At least, what is entropy in probability? So a real quick definition, I guess entropy is a measure of how like distributed the data is in probability. So you can see I have the blue distribution and the red distribution. Which one has higher entropy? Well, the red distribution has a higher entropy, because that is just a more reasonable distribution for grades. It's more, we can reasonably think that, oh yeah, the grades could be distributed this way. And I just got an email, which I don't think you guys can hear because I'm not recording my computer audio, but I am recording my microphone. So I don't think you guys could hear that, but I just got an email. I hope it's not something important, because I'm not going to be able to check it for a few minutes. But anyway, how would I represent the entropy? Well, I would represent the entropy as the number of possible ways I could distribute the data into these bins. So I could say that the number of possible ways I can distribute up the data into, say, the blue one would be the total number of students factorialized over the multiplication of the number of students in each bin. That's the number of possible combinations there are here. So it would just be 500 times 500 factorial. And this is just saying that this is the total number of ways that I can divide up students into these two bins. That's an expression for that. Now, for the red distribution, which has a higher entropy, there's still 1,000 total students, so I would take 1,000 factorial. But then on the bottom, the total number of bins is going to be, there's a lot more, so it's going to be like 100 factorial times 100 factorial times 100 factorial times 100 factorial. And so a generic way I could represent this formula is by saying the total number of students factorialized over the product summation. So this is a product summation from I equals 1 to I equals k, where k is the maximum number of bins, or in this case grades. So in this case it would just be k equals 10 from 1 to 10. And I'll use k and 10 interchangeably from here on out, just for simplicity. But you would multiply the number of students in each bin, the factorial of the number of students in each bin. So this is actually a function of maximum entropy. This right here is in fact a function or an expression of maximum entropy. So are we good to go here? Are we good? I'll say, or it's not a function of maximum entropy, I misspoke. And this is a function of entropy. Now the higher this function is, that means there's more ways to distribute students into all these bins. For instance, there's more ways to distribute the students into the red combination than there is in the blue. But this function, so the maximizing this function will give you the distribution of grades that is most likely, which is what we're going to get to eventually. But for now, let me just focus on making this function into something that's a little bit easier to work with. I have this expression of entropy, but the main issue is this n factorial, well, all these n factorials. Because if you look over here, we're looking at like 1,000 students. That's a lot of students, and NumPy or various calculators or various Python-based calculators can't easily run like 1,000 factorial. There are some ways around it, but just to maybe simplify the expression a little bit, let me go ahead and boil this down into something that's maybe a little bit easier for a computer to work with using something called Stirling's approximation. So I'll go ahead and copy this expression down here, and let's take a look at Stirling's approximation, which I conveniently had the Wikipedia page up. So if you look over here, you can see this function of something or other. Honestly, I don't really know what that graph means. But Stirling's approximation is an approximation of 4 factorials. So this is saying that the natural log of n factorial is just going to be n times the natural log of n minus that number n. And then plus, this is some like term, well, it's not some term. This is a term relating to the error. So I'm gonna go ahead and actually ignore that term, but I will go ahead and copy Stirling's approximation straight from Wikipedia into my thing. And I'll go ahead and say this is Stirling's APPROX, and not a very well written APPROX. But yeah, this is Stirling's approximation. So I can take like this function over here, right? And if I were to take the natural log of it, I could start to work in some of Stirling's approximations, and that would just make it way easier to calculate these factorials. And so if I take the natural log of this whole expression, still maximizing this will still give you the same like maximizing of the entropy. So I can go ahead and say, since this is in a natural log, I can start to break this down a little bit more. I can say that the natural log of n factorial is just going, then I can subtract the summation, and I'm going to start using this pi. This pi means from I equals 1 to I equals 10 or k or whatever. I'm just going to start putting just pi there for the product of the natural log of all, or of the number of students in each group factorialized. So you can see a couple of cool things are starting to develop here. First off is I can start to work in some of these Stirling's approximations, right? So I can go ahead and I see two really easy ways to work it in. So this is just going to be the total number of students times the natural log of the total number of students minus the total number of students minus the product. Now actually, because I multiplied in a natural log here, this product, and I should have done this up here, so this is my bad, but the product is actually going to turn into a summation, because you're turning it from a natural, from a regular, just like from factorial to natural log. So you can go from like a summation to a product. It's all the same with natural log. So minus the summation of, well, let's see, we would have the number of students in each group times the natural log of the number of students in each group minus the number of students in minus the number of students in each group. Now think about it. We have this ni over here on its own, so we could take and summation that out. But if you think about this for a second, the summation of all the students in all the groups is just equal to n. So right here already I get a really great opportunity to cancel some stuff out. I can cancel out this negative n with this ni, and then I am just left with the expression the total number of students times the natural log of the total number of students is going to be, I have to, I guess, it's just going to be the equivalent of that, right? The summation of the total number of students times the natural log of the total number of students. So, where can I go from here? Well, I've talked about how we want to, going forward, maximize the entropy of this function, right? And so if I come down here and I want to maximize the entropy of the function, I can actually eliminate any term that is constant, right? And so n is just one constant. It's not going to change at all. We're not trying to change the total number of students. We're trying to change the number of students in each bin. So for this example, big N is constant. So I can go ahead and cross that out. Well, if I selected the right thing, I want to have a pencil selected. I can go ahead and cross that out because it is constant, right? And so I'm left with, down here, just I want to maximize. So I'll say I want to maximize the following function. I want to maximize the negative summation of ni times the natural log of ni, or the number of students in each grade probability, or in each grade, or with each grade from 1 to 10. So let me go ahead and maybe introduce a new term that should let us do some cool new stuff that's going to be pretty fun. The probability of a student being in a certain grade is just the number of students in that grade divided by the total number of students. That's pretty intuitive here, right? Well, I can rearrange that to say that the probability of students having a certain grade times the total number of grades is going to be the number of students in an individual grade, or in a grade I. So now I can look at this and I can actually introduce this into the problem. So I can say negative summation of the probability of a student having a certain grade times the total number of students times the natural log of the probability of a student having a particular grade times the total number of students. And yeah, I can go through and take all this. Now you'll see right here, the total number of students is still constant. So I can take that outside of the summation here. And then we have the natural log of two things multiplied together. Well, that can actually be broken up into, that can actually be broken up into, what am I trying to say here? This can be broken up into a few different things. So I can go ahead and say the negative total number of students times the summation of the probability that a student has a certain grade is going to, or multiplied by the natural log of pi, or the probability a student has a certain grade, plus the natural log of n. Well, you look right here, now I can sort of break up this summation a little bit more. So I can say negative n times the summation of the probability of I times the natural log of n, which, remember, that's a constant, and something pretty cool is going to form here. And then also have to subtract the total number of students times the summation of the probability a student has a certain grade times the natural log of the probability that a student has a certain grade. Well, if you look over here, the summation of all the probabilities is just going to be equal to 1, right? And then n, so that's the total number of students times ln of n. Well, 1 times that is actually what we have up here that we canceled out for being constant. So if we write this in terms, if we try to write this function of maximum entropy in terms of the probability that a student has a certain grade, we'll just get, these would cancel out anyway, even if we didn't try to maximize it, like if we just tried to write the function. So I can go ahead and cancel this out for being constant / it's just already canceled out by that. Then we are left with a certain function down here. And so my function for I guess not max, but my function for entropy, I think I spelled this correctly. My function for entropy is just going to be negative total number of students times the summation of the probability of a student having a particular grade times the natural log of that same probability. So going back to the prompt, I needed to derive the expression for the entropy of a discretized probability distribution. I used the example of a student grade distribution in terms of the total number of possible permutations of n objects. And yeah, that's what I did. So pretty sweet, pretty fun. This is sort of my final function down here that I can go ahead and I can type it in. I can maybe put that as a function in, put this as a function into Python, and then I can use maybe the sum square error or some other method to minimize it. So with that, I will end the video here. Thank you very much for watching. Thank you all over there. I hope you learned something, and I hope you have a wonderful day. Bye-bye.